Good morning. Thank you for the introduction. And also, I'd like to thank the organizers for setting up this nice conference and inviting me to speak today, and also the nice dinner yesterday evening. So my talk is called The Integrable Bootstrap for AdS3 CFT2 Correlation Functions. And this is based on work together with Burkhard and Alessandro, who are both here in the audience. And in a nutshell, I'd like to introduce to you in this talk the hexagon formalism in the case of AdS3. So, but to do this, let us first take a look what is known about this hexagon formalism in AdS5. And here you basically have by integrable methods the spectrum, which is fairly well understood. And then in 2015, Basso, Komatsu, and Vieira introduced this hexagon operators. So the idea here is that you take a 3-point function and cut this pair of pans into 2 hexagonal patches. And by symmetry consideration, you can fix these form factor for each of these hexagonal patches. And then, yeah, just put it back together and calculate in this way your 3-point function. And in principle, this method is also applicable to higher point functions. So you can, for instance, think about the sphere where you have 4 punctures and then you tessellate it in all possible ways and you have to sum over it and so on. But what you will get is always this hexagon form factor that you can evaluate and then just get the higher point functions. You can also do this for non-planar corrections. So consider a homogeneous function or homogeneous, so like a torus with a 2-point function or something like this, and then you tessellate it as well into hexagons. So this is really nice formalism. And to consider wrapping corrections, you basically place virtual particles on these dashed lines here. So there's the talk by Benjamin Basso from Monday. So this is ongoing work and still an open problem, more or less. So the question might arise, can we study another and maybe simpler setup with this hexagon formalism? Well, and another setup, at least, is AdS3 string theory. So here you have 2 main parameters, K, which measures the amount of Neveu-Schwarz-Neveu-Schwarz flux, and H, which measures the amount of Ramond-Ramond flux. The spectrum here is classically integrable and believed to be also integrable at quantum level. You can now look at a few special cases, since in general these 2-parameter space of these K and H is kind of complicated. And there you have the pure Ramond-Ramond limit, where the NS and S flux just vanishes. And this case is most similar to the case that you have in AdS5. And then there's also the pure NS and S limit, where the Ramond-Ramond flux vanishes. And here the spectrum is given by a level K Wess-Witten model. Then even more special in the NS and S case, you have this case for K = 1, where the Wess-Witten model becomes basically a free theory. And then one further advantage in the NS and S limit is that the TBA is known for all K, and wrapping is simple. So since wrapping is simple, this might be a setup where you want to study hexagons. So let me give you an outline of this talk. So first of all, I would like to review a little bit of the integrability that we know for AdS3 crosses 3 crosses 4. So this is really the string theory that we will specialize on here. And then afterwards, set up this hexagon operators, show you the matrix part, and also what we know about the addressing factor. And then after having done all this, let us perform an explicit check to see whether this formalism does really gain us something. So in this case, this will be for protected 3-point function, but you'll see. And then I'll give a brief conclusion and an outlook. Okay, so let's first take a look at the supersymmetry algebra. And the bosonic subalgebra is given by SO2,2 and SO4. And you can think of these as basically the isometries coming from AdS3 in the case of SO2,2, and SO4 is basically coming from DS3. You can then decompose those in 2 copies of SU1,1 and 2 copies of SU2. And if you now add supersymmetry, you will get 2 copies of PSU1,1/2. So we will call them left and right. Of course, there's also the T4, but this gives us just shift isometries and is not so important here. So I have the picture. Okay. So let's take a closer look at these 2 copies of PSU1,1/2. And for instance, you could take a look at the how they contribute to the light cone Hamiltonian. So in the case of the left copy, this contribution is given by a combination of L0 and J3. So L0 is the SL2 Cartan charge, and J3 is the SU2 Cartan charge of these of the bosonic subalgebras. And you also have this for the right copies. Here we denote the generators with tildes. The BPS bound is then given by H or H tilde larger or equal to 0. And the next step, or the next thing that you could ask is, okay, what is the amount of supersymmetry that commutes with this H and H tilde? And what you'll find is that half of the supercharges commute. So in total, you have 16 supercharges, 8 in the left copy, 8 in the right copy, and now 4 in each copy commute with this H or H tilde. These charges also carry some SU2 index and transform in the fundamental representation of an SU2. So taking a closer look at these commuting supercharges, what you'll find is that they form 2 copies of PSU1/1 with SU1 charge H in the case of the left algebra, and also 2 copies in the case of the right algebra. So in total, you have 4 copies of PSU1/1. And then you also can add the central extension in this way. Okay, so we have this 4 copy of PSU1/1 centrally extended, and this is kind of similar to the structure that we have in AdS5, where we have 2 copies of SU2/2. There is then kind of sufficient to just consider one of these copies to find, for instance, representation and then the S matrix and so on. So let's kind of copy it here and just take half of these algebra. So we just consider 2 copies in the following way. So let us introduce these 2 copies with the generators QS and Q tilde and S tilde, such that we have these anti-commutation relations together with the central charges. And then you can get back these 4 copies by just taking the tensor product. In this way, you can also get all the relevant representations here. I'll come to the representations in a moment, but first let's take a look at the combination of the central charges H and H tilde. So you could take the difference or the sum and then express this in terms of the parameters of the theory. So you will see that here K and H show up again. So these properties of the string background. But there's also an M. And if you look at this dispersion relation, you see that the M plays the role of a mass. And now we can distinguish the following cases. So for M equals 0, we will call a representation massless. And for M a positive integer, we will call it left. And for M a negative integer, we will call it right. So here we will only be interested in M equal to 0, +1, or -1, since all the higher masses correspond to bound states. So we are interested in fundamental particles. So now let's take a look at the short representations, which are 2-dimensional and consist of 1 boson and 1 fermion. And then the following, I will denote the highest weight state by the straight phi and the lowest weight state by this curly phi. And then, of course, you can use the supercharges to go up and down between them. You are here still kind of free to choose what should be your highest weight state, or what should be the statistics of your highest weight state. So you can choose it to be a boson, then the lowest weight state will be a fermion, or you can choose the highest weight state to be a fermion, then the lowest weight state is a boson. And there are 4 representations. So one is left, where the boson is the highest weight state, one is right, where the fermion is the highest weight state, and then we have 2 massless. One of them you can, so in the 2 massless, one of these 2 massless has the boson as the highest weight state, and one has the fermion as the highest weight state. Okay, and from these short representations, we can now build the representation of the 4 copies of PSU1/1 just by tensoring them together. So here is, for instance, the left representation, where you tensor together 2 fundamental left representations. The structure here is not so important. So I mean, this tensor product structure is not so important. What I want to show is the general structure. So you have a highest weight state and the lowest weight state, and in the left representations, these 2 are bosons. And then you have these fermions in the middle, which once again carry this SU2 index that also the supercharges carry. It's similar for the right representation. Here you kind of get a Z tilde as the highest weight and the Y tilde as the lowest weight state also both of them are bosons, and then fermions in the middle. There is also a discrete symmetry, the left-right symmetry. So basically, you can just exchange the left algebra for the right algebra. And since these are just names, you can also kind of later on just swap left particles for right particles. And then we have the two masters representations, which carry an additional SU2 index. So this SU2 circ is what it's called. So these SU2 commutes with all the algebra that we introduced so far. So you could also ask, well, but why do you write two representations here? The reason is that you can, in fact, write just one tensor product representation and use this representation for everything else, and then keep in mind that you have these additional SU2. But we found it convenient to really write down two of them and write them in a slightly different way, since that makes your life easier later on with the hexagon. But the important thing here is that the highest and the lowest weight states are fermions, and the states in the middle are masters bosons, which carry both the SU2 circ and the SU2 bullet index. And you can think of these two SU2s as coming from the T4. Okay, so then the last ingredient that one might need is the S matrix and scattering. So the full S matrix can be obtained as well in a tensor product form, where basically this S scatters on the first copy and this S scatters on the second copy. And you can then determine this S from symmetry generations by demanding that it should commute with the generators. In this way, you can find S up to an overall prefactor sigma, the dressing phase of the S matrix. And I told you that we have 4 representations, left, right, and 2 masters. So in total, we can have 16 blocks of different things that might happen during the scattering. To simplify the notation a little bit, I'd like to introduce you some new notation. I mean, not new, but you haven't seen it in this talk before. So to distinguish, we will use explicitly the left-right symmetry to distinguish between all the different things that can happen. So in the massive case, for instance, we have these 2 bullets if we're talking about left-left or right-right scattering. And if there's a tilde, then it's left-right or right-left. The master sector is just indicated by these 2 circs. And then in the mixed mass sector, you have these bullet circ to indicate it's the massive masters, sorry. And then the circ bullet to indicate that's masters massive. Yeah. And then there's also a proposal for the dressing factors for the pure Ramond-Ramond and the pure SNS case. But we won't need the explicit form here. So what we will need of these dressing phases is they are generally pretty complicated and have these branch cuts on the Tchaikovsky plane and so on, but we only need their properties of unitarity and anti-crossing. Okay, so that was the brief review of integrability. Let us take a look at 3-point functions. So we would like to consider the following setup, where we have one operator sitting at 0, 1 at 1, and the third one at infinity. And we want to get there by starting with an operator at the origin and then translating it to these other positions. And we want to do it in such a way that it preserves as much supersymmetry as possible. And therefore, let us introduce the super translation generator, which basically consists of this translation here and then also an R-symmetry rotation. Here's some kappa, and this kappa is some complex numbers. So a priori, it's not clear what it should be, but it will be in a couple of slides. And now you can just go ahead and construct your 1-parameter family of operators by taking this exponential and just moving your operators to the point you want to have it. Okay, now that we have this super translation generator, we can ask, what is the commuting subalgebra? And we will already call it hexagon subalgebra. And it's pretty straightforward to just work it out by hand and find that these combination of the supercharges commute with this T kappa. You can then also work out the anti-commutation relations, which basically all vanish, except for this one. So if you take Q with Q tilde, you will get some combination of the central charges of P, so the central extensions of the 4 copies of PSC1/1. And therefore, let us also introduce this central charge here, which just captures this this combination. Yeah. So now let's get to the bootstrapping. And the bootstrap principle here is that the hexagon should preserve this symmetry algebra that commutes with the twisted translation, with the super translation generator. And the idea is that acting with a supercharge on any state psi, this should be annihilated when you afterwards contract with the hexagon form factor. This should not only hold for Q and Q tilde, but only for a combination of both of them. So like central charge C that I just introduced it as this combination. But the central charge acts diagonally and independent of flavor. So this should vanish in general. But this, if you take this combination of the central charges, then this will only happen for physical states. So when C and C dagger vanish. But you can now, I mean, so I should say that this is too strong of a requirement for the hexagon to give something consistent. So we want this central charge also to vanish off shell. By choosing C and C dagger to be real, we can set kappa squared to 1, and then the central charge vanishes also for all the off shell states that we can consider. And this way you can now go ahead and just act with this diagonal charges on the states. And you'll find some linear system which you can solve and find the following relations for the one particle form factors. And what you see here is that basically the hexagon form factor of the highest weight state is related to the hexagon form factor of the lowest weight state in case of the left representation, but also in case of the right representation. And if you look closely, you will also see that left-right symmetry applies here. So just placing a tilde or removing a tilde kind of gives you the same if you normalize in the correct way. And in the master's representation, you have these two fermions, so the highest weight state and the lowest weight state once again, which are related by this form factor. And all the remaining form factors vanish. So in the massive case, the fermions, and in the master's case, the bosons. Okay, so having understood this and worked out the one particle form factor, you can now consider two particle states and basically apply the same reasoning, work out this linear equations. And what you find is that the two particle hexagon form factors are given by S matrix elements. So the S matrix, the Borsato-Olsen-Sachs-von S matrix elements up to scalar prefactors, since these are not determined. I mean, you can just write a big list of all these elements that you get, or you try to work out some formula which relates everything to the S matrix, since it seems to want to be related to the S matrix. And this can be done in the following way. So let us consider a generic excitation of these 4 copies, which we will split once again in the tangent product of the representations of these 2 copies. So psi A tensor psi prime. This lives in the first, this in the second copy. And now you evaluate the hexagon form factor in the following way. Don't worry, I'll take you through it. So we have these 2 particles here and write them in this tensor product notation here. And then what you do first is you move all these particles without the prime to the very left. So for instance, this psi B, which used to be here, goes to the left. And by doing that, you might pick up some fermion signs. So the first thing that you overtake is A prime. So you get A prime times FB. And then you also kind of reorder this state here. So you also overtake the FA. So it's FA times FB. And then afterwards, you scatter with the S matrix on this primed state here. This gives you some S matrix element. And all that is left to do is just to contract with the one particle form factors that we saw on this slide before. So basically you contract this psi Q on psi Q and P and P. You can also think about this pictorially. So here you have these unprimed excitations or components, and here you have the primed. Then you scatter with the S matrix and just contract everything on each other. Notice that we introduced here a contraction operator, which was not the case, or which was not necessary in the case of the AdS3 hexagon form factor. And this is due to the case, so basically we did it to get the statistics right. But this is due to the case that our massless one particle form factors are associated to fermions. So the highest weighted in the masses case are these fermions, and getting a hexagon form factor, you might ask, well, okay, what is the statistics of this form factor now? And by introducing this contraction operator, you kind of get rid of this ambiguity, since you have now these basic derivations. And then you just multiply by the corresponding one particle hexagon form factor. Okay, and in this way you could, in principle, go on and take a look at 3 particles, 4 particles, and many more. The issue is that the symmetry algebra is not constraining enough to fix you all of these elements here. So what you do is you try to write, you try to pose in self-consistent ansatz to work out these many particle form factors. So let's take a look at this. So the idea is basically the same. You take all these n particles, you move all the unprimed to the very left and reorder them from Pn to P1, which introduces some bunch of fermion signs. Then you scatter with the n particle S matrix on this primed state here. And afterwards, you just apply the contraction operator. So and the nice thing is that this S matrix factorizes due to the Yang-Wechsler equation, and instead of n particle scattering, you just have multiple two particle scatterings. And in this way, you can evaluate this, and also this ensures that, I mean, this factorization ensures that this is also compatible with the symmetry constraints that we have. Okay, well, this fixes the hexagon form factor up to the scalar prefactor h, which plays kind of a similar role like the dressing phase sigma in the case of the S matrix. So to simplify notation in the following a little bit, let's once again introduce this following normalization. So if we take a look at these 2 particle states here, we just normalize them in such a way that they give this just this H phase, H bullet bullet, since it's left left or right right, or in the left right right left case, H tilde bullet bullet. Then in the masses case, you get this H circ circ, and in the mixed mass, you get bullet circ or circ bullet, depending on the hexagons that you're considering on the 2 particle states. Okay, and now let's impose some constraints to fix this, well, I mean, to get an idea of what this H should be. And the first thing is the Watson equation. So the Watson equation states that when you scatter 2 particles with the full S matrix, including the dressing factor, then it should not change the form factor, so the hexagon form factor. So pictorially, you have this hexagon form factor here, and scattering with a full S matrix should give the same hexagon form factor. And if you work this out, what you'll find is this relation between HPQ over HQP, which is related to basically sigma squared. This equation can be understood in a very straightforward way. So this HPQ comes from this form factor on the left-hand side. Scattering with a full S matrix, which is 2 copies of the S matrix, gives you 2 times this dressing phase, so you get sigma squared. And then afterwards, since the particles are scattered, we get HQP from evaluating the hexagon form factor on the right. So in this way, we can also find this for in the massive, mixed mass, and in the masses case. So this is the first constraint. The next one is the decoupling condition, which states that whenever 2 particles form a singlet, they should decouple from the hexagon. Once again, in the picture, these 2 particles, P1, P2, up here, kind of form these singlet, and then they decouple from the hexagon, and you have just to evaluate this Q1 to Qn particles. So the singlet must be annihilated by momentum and energy operators, and therefore one of the momenta has to be crossed. So basically you have a particle-antiparticle pair sitting there. And if you work this out, you basically find a crossing equation. So you can scatter a singlet with the S matrix as well, and then you'll find the crossing equation for the dressing phases. Here, the dressing phases for us are these hexagon scalar prefactors, and the right-hand side is just the dressing equation. We will also introduce these Shukovsky variables, which can also be expressed in terms of the parameters of the theory and so on, but this is also not that important here. Okay, so we got a crossing equation on H. And the last thing that we need to consider is cyclic invariance. So the idea here is, in the end, to evaluate a hexagon form factor, you have to bring all the particles to the same edge. But the hexagon should not know which edge we are talking about. So moving particles from one edge to another, so like this PQ to this edge, P2 gamma Q2 gamma, sorry, should not change the form factor. Also, I forgot to say this. Moving particles from one edge to another basically corresponds to a crossing equation. So, not crossing equation, to crossing. So moving this particle from here to there, you get P2 gamma. And then on the other hand, moving just one of those particles once around the hexagon should also not change the form factor. So we could, for instance, take this Q and move it once around to Q6 gamma, and this should yield the same. So on the left-hand side, we have, for instance, here a little example with two massless fermions, and then moving one of these fermions around, you have to conjugate it. It's now a chi tilde, so the lowest weight state at Q6 gamma and a chi. And then you can just evaluate this form factor. On the right-hand side, you will get some matrix element, and then also this H at Q6 gamma. And now we can use the crossing equation that we worked out on the slide before and plug this in here to find some relation for HPQ times HQP. So this is just given by this rational expression here on the right-hand side. Okay, so let's wrap up what we have. So we have the Watson equation, which relates HPQ over HQP to sigma squared, so the dressing phase of the S matrix, which also can be rewritten in terms of this sigma squared and some Sukowski variance, sorry. And then we have the gamma cyclic invariance, which relates HPQ to HQP. And now the question is, what might be a solution for this H? And you basically see it. Just multiply these two equations together and take the square root, and you get HPQ. Well, of course, you have to be a little bit more careful about the cuts of this root and so on. But this is basically how we managed to find these scalar prefactors. Also in the massive case and the mixed mass case. Okay, so we are good to do some explicit checks and see whether this formulation really yields something. So and therefore, let us consider protected multiplets. So in AdS5, for each value of the R charge J, there's one BPS operator. Here the situation is a little more complicated. So we have basically two R charges, the left R charge J and the right R charge J tilde. And for every positive integer J, you then get this diamond of 16 BPS multiplets. And to make things even more complicated, these multiplets can also mix among each other as J changes. So for instance, take a look at this middle ones here, where you have J minus 1 and J minus 1/2 and J minus 1/2, J half and J half, and then J plus 1 down here. And if you now shift this one to J minus 1, keep this one at J, and shift this one to J plus 1, they all have the same J charge, and in principle, they could mix among each other. Fortunately, this guy here, this multiplet here, and this multiplet here, they do not mix. So these are the ones that we want to consider in the following. So we now have also to translate this back to this picture of integrability that we were using so far. And the first thing is that we have, basically we can think of these multiplets here as the BMN state with charge J half sitting right here. And now by inserting all the different massless fermions at zero momentum, this is important, you can basically generate all these 16 multiplets. So the question is which massless fermions at zero momentum should you insert to get these multiplets? And therefore, let's take a look at this table, which is taken from a paper of Andrea and Alessandro. And the thing is that these massless fermions are chiral, depending on their momentum. So to construct these BPS operators, what you basically have to do is to get this plus minus, where you shift the J charge by plus 1/2 and the J tilde charge by minus 1/2. You can now look at this table and just identify, well, okay, so we have to place chi1 tilde with the momentum going to 0 from above, and we have to place chi2 tilde with the momentum going to 0 from below. And then also for this minus plus case. So these are the correlation functions that we want now to consider. And basically there are two cases. So the first case is all of the three operators are the same, so minus plus. And the second case is one is different, so plus minus. You would now ask, okay, what about all the other cases? But once again, here, this is just some you exchange the left and the right J charge. And by doing this, you can basically generate the other ones. So you exchange the left and the right J charge and also the algebras. And these correlation functions are worked out and can be found in several places in the literature. And what you see is that here's some prefactor and also some Clebsch-Gordan coefficients. Those won't be very important in the following, but they're also fairly simple here. And then you have this combination of these values J1, J2, and J3 in here with pluses and here with a minus sign. And now we want to try to calculate this by using the hexagon formalism. So using the hexagon, you kind of take these three operators with with the fermions, so chi1, chi2 sitting on the first operator, then also on the second and on the third, with momentum P1, P2, and P3, and you distribute these particles in all possible ways over the hexagons. So I will explain this equation here a little bit better in a moment. But first, let's take a look at the second correlator, and here it's kind of similar, except that the last operator carries chi tildes instead of these chi's that we have here. Okay, what we do then is now I'd like to explain this equation a little bit better to you. So you have this 3-point function, and you cut it into the two hexagonal patches. So let's first look here, the two hexagons, and then you sum over all the ways in which you can distribute the excitations, so the masses, fermions, and zero momentum, on these two hexagons. So in this picture here, you have the front hexagon and the back hexagon, and in the first case, everything is sitting on the first hexagon. But then in the next step, one particle moves to the back hexagon, and you get this weight factor in front here. So this is given by this W. Then the other particle moves to the back, or both of them. So you have kind of 4 possibilities for every particles, for every operator. And this gives in total 64 partitions over which you have to sum. So it's quite a lot to evaluate here. And the thing is that, as I said, these particles are massless fermions at zero momentum, and the question is now, well, how to take this zero momentum limit in a good way, since in principle you have 2 subtleties. So when the momentum goes to 0, you might find poles, and then on the other hand, all these operators kind of have the same, all the particles have kind of the same momentum, and like in the decoupling condition, this could also form poles and give you singularities. So we kind of need to be little bit careful to take this momentum to 0 limit. And also the particles, this hexagon formalism should not depend on the way that we constructed the operators. So this means specifically that it should not depend on the order in which you place the particles on the operator. And this is indeed the case as long as the beta equations are satisfied. And since we're considering free particles here more or less, the beta equations become really simple. So this means for the momentum that it should basically be given by 2 pi over this J charge of the operator. And to get away with this coincident limit of the momenta, let us introduce this epsilon and epsilon k and redefine J and P in this way. And then by setting these P's here on the right-hand side all for the same value and taking this limit epsilon to 0, you basically get this first the coincident momenta limit, and then you can take P to 0 and get this zero momentum limit. For the evaluation, there are also two more nice properties. The first thing is that the correlation functions are protected for any value of h and k. And the second thing is that the kinematics of the massless particles do only depend on this ratio h over k. So in evaluating everything, you can basically write it with this h over k coupling instead of h and k. Okay, you can then just go ahead and do this and take a look at what this hexagon formulation yields for small p. And in the case of the first correlator, you find the J combination in the way that you want it to be, times this p squared. And also for these second correlator, you find it with the minus signs here and there in the way that we want it to be. The issue is that, I mean, maybe not the issue. So you will notice that the prefactors are not what you expected from the CFT methods. But this is not too big of an issue here, since the ratio matches. And this is also kind of the case in the case of the AdS3 hexagon. So also there, if you consider a 3-point function with unprotected operators, you usually normalize by a 3-point function of protected operators. But the hexagon there is very simple, since there are no excitations on these protected operators in AdS3. Yeah, so this basic first check worked, and we find indeed what we expected, or what we wish to find from the CFT. And I'm a little quick, but let me already get to the conclusions and the outlook. So we saw that the hexagon approach for the computation of 3-point functions by integrable techniques can also be applied to the case of AdS3 crosses 3 cross 4. And the structure of this hexagon form factors is entirely fixed by this symmetry considerations. So we took a look at this translation generator, and then found the commuting symmetry algebra, and this fixed the matrix part of the hexagon form factor. And then by these constraints, so Watson crossing and cyclic invariance, we also managed to relate the dressing factors of the hexagon to the dressing factors of the S matrix. And in principle, this method is valid for pure Ramond-Ramond flux as well as mixed fluxes. And this is the first example where you can apply these hexagon tessellation to a string theory other than the original AdS3 crosses 5 case where this formalism was proposed. And we also did this successful check of the resulting machinery with the resulted 3-point with this protected 3-point operators, which kind of nicely matched the results. Okay, so what can we do next? So for instance, we can now, with this hexagon approach, since it's valid for mixed flux as well, study mixtures of an SNS and Ramond-Ramond background fluxes. The issue here is that the dressing factors are unknown, and probably they are highly non-trivial. One could then also take a look at these pure cases and study, for instance, pure and SNS limit. But taking this limit is quite tricky, which is the pity here. But then on the other hand side, the wrapping should be simple, and it should also be possible to compute the results by CFT and then have a way to check it. You could also take a look at the pure Ramond-Ramond case, but as here the dressing factors are already proposed, but the downside is that you cannot compare with CFT results. Of course, you can then also think about doing what's already been done in the case of AdS3 and take a look at higher point correlation functions or non-planar corrections. So for instance, take a look at 4-point functions of VPS operators. Yeah, and if AdS3 is, so this would wrap up AdS3 and things that we would like to do in AdS3. But then, of course, you can also go further and ask, well, which other backgrounds are there that can also be used to try this bootstrap approach and provide a hexagon formulation of the theory. So many interesting things to be considered and to be done. And with this, I would like to end my talk. Thank you.
Questions?
Thanks for the very nice talk, and it's great to see that the hexagon apply as well in AdS3. I had some question about your ansatz. I wanted to know how much did you explore its consistency in the mirror channel. In particular, I saw that you had some square roots, and I was wondering if, you know, after continuation to the mirror channel, the square root will cancel out, or if they will be present somehow in the hexagon form factor. And relatedly, I wanted to know if you looked at the massless mode, and I wanted to know if the massless mode, for instance, are small in the mirror channel, or if they can possibly be enhanced.
Okay, so to the first question, so the self-consistency checks, it's what we call it. So we tried quite a few things. I'm not sure. So what was the question? So in the mirror channel.
Yeah, so I saw that in your ansatz you have some square roots. You have square root of differences of Joukowski's, and you know it could happen that they are fine on one Riemann sheet.
Yeah.
That the square root, for instance, if you expand at weak coupling, the square root will you will have the square root of something that is like a perfect square or something like that. But if you analytically continue to the mirror sheet in a particular way, and there are many sheets, then possibly, you know, this cancellation could be not working as nicely, and then you will have to interpret this singularity if there is a square root that is left there.
Yeah. I think it was someone. Go ahead.
So yeah, if you can go back to where you showed these, because I think I understood what yeah, a bit forward. I think maybe, I think this might be one of the things that stood out to you, right? So this is a sort of a nice symmetrical way of writing it, but it turns out that this is for the massless guys, and these the square root is not really there because x plus and x minus are actually related. So as it turns out, if you write it, there is this very nice parameterization that was invented by Alessandro Torielli and Andrea Fontanella, and which is relativistic and so on. And you realize that this thing is actually perfectly nice, and it's a rational thing.
So basically,
it's a bit of an accident of how we wrote it, which looks nice in a way because it's nice and symmetric, but it's sort of, it's a bit, it's a bit unfortunate because indeed, analytically square roots, you'd rather not have them.
So if you work it out in this parameterization, so basically what you get is you have this parameters gamma of p and gamma of q, and basically this whole square root reduces to some tanh of gamma p minus gamma q. So this whole parameterization, at least in the massless Ramond-Ramond limit, can be written in terms of differences of this qp minus gamma p minus gamma q. The square root basically becomes a tanh.
And okay, my second question was related to the behavior of these factors in the mirror kinematics. So if you think about, you know, going one step further and go, calculate structure constant, including the mirror corrections, I wanted to know if you look at it and if it's clear that they will be suppressed with the coupling constant. What is the typical scaling that you will find and so on, if you looked at it?
Yeah, we haven't taken a look at the mirror channel at this stage. So this is basically really just the operators with the excitations, and then this would be also the next things to consider. So also looking at the bound sets, the virtual particles.
Okay, thanks.
Thank you.
More questions? So I would have a question. So is this formally also valid for non-protected operators? I mean, non-protected correlators?
So I'm not really familiar with the details, but I mean, if you can tell me what kind of excitations we should place on the operators, then I guess, if you really can identify this in some way, then this should be possible to, just as in the case of AdS5, tessellate all the excitations in all the ways that this can be done, and then you have to sum everything up, and it might be kind of not very nice, and many terms to consider. I mean, already here you saw that for these protected BPS operators, you get the 64 partitions which you have to evaluate and so on, and then be careful about the limits. But in principle, I would hope that this might be possible.
Thanks.
Actually, there's various authors in this project, and we did not always agree on which branches to actually choose for these routes, right? I mean, so in actual cases, we're going to have to see, I think. The difficulty being also the scarcity of things to compare with, right? So I asked Alessandro, like, what can we match on? And it seems that this thing by Pacman and Seva, and that's essentially it for the moment. So if we start playing with the wrapping, it's sort of like a wild card, right? I mean, you don't really know what it ought to be. I mean, so one question to the audience then, what else can we compute that can, I mean, there's many experts in AdS3 that we can match. And the other one I was going to ask you, I mean, we did this in many ways. The first one probably being, you want this to factorize, so you write all sorts of monomials that you can get with these Shukovskis and so on, and then you see quite quickly that you get these roots, right? So what did you actually do? The paper says the simplest solution is. It does not say it's the unique solution.
Sorry, can we have the second microphone? Please.
No, I don't have anything special to say about uniqueness. I mean, it's clear that the bootstrap axioms alone will not give you a unique answer. There are ambiguities. They are well understood in some situations, like for form factor of local operators or this kind of thing. Again, well, it depends on the theory, where you can parameterize your ignorance or write the most general ansatz and eventually try to pin down the one that is associated to the case you're interested in. In this setup, where we don't have like boost symmetry and we have complicated kinematics and dynamics, we don't know how to write the most general possible solution. And then eventually, corner the one that is the most, I don't know, the one. So, but often, the simplest one, the one you can't find, ends up being the right one, if you're lucky. And okay, that's essentially what we did. So
yeah. I mean, so one experiment I did when we were sort of desperate about getting this Pacman and Seva result right, because the limit is very subtle, right? Was that I was using religious cyclicity. And then you assume that it's monomials, and you just say, I want to balance the Shukovskis up and down, right? But that's a condition that comes from nowhere. Maybe that the expansion makes sense at recoupling or something like this. Otherwise, you've got no reason to believe this, right? But as you say, I mean, the simple one. But this is very much constrained. I mean, apart from the science, I don't think there's much that you can twist on it. But the science and mirror, no idea. To be tested, but against what? I mean.
Okay, I think we also have questions on Zoom.
Oh, hi. Thanks for the nice talk. I guess I wanted to understand a bit better precisely this transparency you have here that people asked about. So I can see how that square root can disappear with this nice Fontanella-Torrielli parameterization for massless Ramond-Ramond modes. There is no such parameterization away from the pure Ramond-Ramond point. And also for the massive guys and the mixed max guys, this wouldn't exist in the Ramond-Ramond case. Can you comment a bit more?
Okay, yeah, thank you for the question. So you mean like these other H factors that we have here in the massive case. So indeed, we just kind of worked them out and did not do any further checks since. I mean,
I think the question was about the mixed flux, no? Was it,
yeah. So, but also away from the pure Ramond-Ramond, right, where you do not have these. Yeah, we do not have these nice. Okay. So also for the master, yeah, okay. We do not have these nice parameterization. Yeah. Yeah, this is indeed a good question.
So, sorry, I just want to make a comment. If you look at the formula, just send x to 1 over x is still a square. X minus is 1 over x plus. This thing is still a square, right? You just collect.
But that's a feature of the pure Ramond-Ramond case.
No, that's still true, right? You just have this left and right.
No.
I thought it was in our paper, but sure.
I don't think so. I think, I mean, for physical momenta, is that what you mean?
I didn't hear that.
For physical momenta?
I didn't hear that.
For physical momenta, in the pure Ramond-Ramond case, that is true, but I'm not sure it's true for physical momenta in mixed flux.
I think so. You have in principle a left and right, x pluses and x minus. You remember, right? It's because of the parity breaking, and the x plus massless goes to x 1 over x minus massless. So you would have to decorate that formula with lefts and rights and so on. But mutatis mutandis, it will still work, I believe.
Sure, because for massless modes, I think you can write everything just in terms of left movers. So I think probably there will be a way to write it, but I basically, I mean, as you remember, you can write everything just in terms of massless left modes.
Right, but still, even in the mixed mass, there is still a constraint more for massless than there is for massive, right? It's not really a true Zukowski plane that you have, and that's sort of what still allows you to simplify that expression, I believe.
Anyway, I'm not sure, but I agree that probably if there is a unique analytic continuation in Ramond-Ramond, then there probably is one in mixed flux, but it's just not clear from the formulas here at all why that would be the case. So it's probably worth spelling out a bit more. And indeed, yeah, for the massive. But already, I think the mixed flux already looks there. If you believe there is such an expression for mixed flux, then there will be a much nicer way of writing it than in terms of the square root. So it may be worth checking.
So there is also a question in the chat. How much is known about 3-point functions in the pure and SNS case? CFT gives the exact quantity in the 't Hooft coupling.
Yeah, sorry, I mean this is kind of beyond my knowledge at this moment.
Yeah,
yes.
I mean, okay. So in the pure and SNS case, essentially everything can be computed exactly, I mean, via the RNS formalism. So this would be the perfect scenario to cross-check stuff with the hexagon formalism. I mean, anything you can compute with this hexagon formalism can also be computed in the RNS formalism at pure and SNS flux. So yeah, that would be a very interesting direction, I think.